Welcome to solverfy.
In this problem on the topic of oscillators, we want to find the total mechanical energy as a function of time for a lightly damped harmonic oscillator, and we want to show that it is given by the expression that is provided. We also want to show the fraction of total energy lost per period is given by the second expression that is provided. Now, for the lightly damped or harmonic oscillator, we have b squared to be much less than 4mk, which means that b squared over 4m squared is a lot less than k over m, which means that our angular frequency, we'll call it omega prime, is approximately the resonance frequency omega naught. Now we assume also that the object starts to move from maximum displacement. And so the displacement x is equal to a naught e to the minus bt divided by 2m times the cosine of omega prime times t. And the velocity v is simply dx dt, or the time derivative of the expression above for the displacement, and so this is minus b over 2m times a naught e to the minus bt over 2m cosine omega prime times t minus omega prime a naught e to the minus bt over 2m times the sine of omega prime times t. And so we can write this to be approximately minus omega naught times a naught e to the minus bt over 2m times the sine of omega prime times t. Now that we have expressions for x and v, we can write the energy E to be a half kx squared plus a half mv squared. And so this can be written as a half k a naught squared e to the minus bt over m cosine squared omega prime t plus a half m omega naught squared a naught squared e to the minus bt over m times sine squared of omega prime times t. And so we can write this as a half k a naught squared e to the minus bt over m times cosine squared omega prime times t plus a half times k a naught squared e to the minus bt over m times sine squared omega prime t. And we can see that this simplifies quite significantly to a half k a naught squared e to the minus bt over m, since cosine squared theta plus sine squared theta should give us 1. And this is simply E naught e to the minus bt over m as required. Next, for part B, we want to show that the fractional energy that is lost per period, delta E over E, is 2 pi b over m omega naught, or 2 pi over q. Now, the fractional loss of energy during one period is as follows. Note again that we use the approximation that b over 2m is a lot less than the resonant frequency omega naught, which is 2 pi over the period t. And so this means that b times t over m is much less than 4 pi, which means that bt over m is less than 1. And so the energy change delta E is equal to the energy E minus the energy E at time t plus a period capital T. And so this is equal to E naught E to the minus bt over m, as we've shown above, minus E naught E to the minus b into t plus the period capital T over m. And so we can write this as E naught e to the minus bt over m multiplied by 1 minus e to the minus b t capital T over m. And so the change in energy over the total energy, which is the fractional loss of energy delta E over E, is E naught e to the minus bt over m into 1 minus e to the minus b capital T over m, and all of this divided by E naught e to the minus bt over m. So we can see that this simply becomes 1 minus e to the minus b capital T over m, which we can write as an approximation of 1 minus 1 minus bt over m, which is simply bt over m. And bt over m is b times 2 pi divided by m omega naught, which is simply 2 pi divided by the quality factor q as required.